Welcome to Heat Exchanger tutorial part 3. So for part 3, I just want to focus on tutorial 7. Okay, so tutorial 7 is actually the repetition of tutorial 6 for NTU method. Okay, not tutorial 7, but the repetition of tutorial 6, because this is tutorial 7, you want to repeat the tutorial 6. So in this case, I just want to explain on the confusion that arises from some of you when we should calculate, when we should use the overall area. The overall means the area of 200 tubes, or when we should calculate the area for only one area. Okay, the answer is for calculation of resistance, okay, and also for calculation of the overall coefficient. So this one we consider for only one tube or one area of the tube. Okay, but for the effectiveness, okay, for the effectiveness, we calculate this for overall tubes. Okay, so in this case is 200. So for effectiveness, we must calculate for overall tubes. So why that is the case, to explain further, I want to show you this slide. So again, sketching the problem is the first part or the first step. Okay, so I think you all know how to calculate or how to sketch the problem, and also to illustrate and label the problem. Okay, so in this case, first I wrote down this now, calculation of area for one tube. Okay, if for 200 tubes, the inner surface area should be multiplied with 200, because you have 200 tubes. So from this you get about 32 meters squared. And for outer area diameter, also you multiply with 200 tubes. Okay, so you get almost 50 meters squared. So 32 and 50 meters squared. Then, okay, let's say you say for the resist, because just now this is like a step 2, right? And this is step 3. Okay, let's say just now I told you that the area and also no, the resistance and also overall coefficient, you must calculate for only one tube. But let's say you want to consider for overall tubes, which is 200. So what you do is, the resistance one here, okay, the area here is for one tube, so you multiply both with 200. So that means your answer here is you're going to divide with 200, right? So same here for R2, okay, because here is length for one tube, so you must consider the length for 200 tubes. So when you put 200 here, you put 200 also here. Okay, so same for resistance 3. So this is area for one tube. So you want to consider area for 200 tubes. So therefore here you also must consider area for 200 tubes. So by doing so, actually the answer you have before, okay, you just divide it, because here it is under the part under the line here, okay, the divided line. So you must divide with 200, also here and also here. So that means that the total of R you get, you can divide with 200 for 200 tubes, right? So you get 1.68 10 to the power of 4 Kelvin per watt. Okay, so let's say you already considered that for the total area for the total resistance, right? So for the overall coefficient, which is the U value, so let's say you want to consider for overall area. So that means here you multiply with 200. And if you want to consider for overall resistance, that means because the overall resistance here, you need to divide it by 200. So that means here you put 200. So you see that you can cancel these two values out. So that means the overall coefficient, either for one tube or for 200 tubes, it still gives you the same answer. Okay, so therefore you don't need to confuse, right? So therefore, for overall coefficient, whether it is one tube, 200 tubes, or n number of tubes, actually it gives you the same value. Okay, so therefore, if you want to calculate A here, that means you just take the A for one tube, the area for one tube. Okay, same goes to the R. So that means in order to do that, the resistance here, you don't need this 200 here, right? You don't need this part. Okay, if you don't consider this part, okay, so if you don't consider this part, so this should be your answer, 0.0337. Okay, this should be your answer. If you use here 0.037, okay, and you can just use area for one tube. Otherwise, if you want to use the resistance, total resistance for 200 tubes, which is 1.685 times 10 to the power of minus 4 here, then you should consider here for 200 tubes area. Okay, so but the thing is, it will end up with the same answer. Okay, so therefore don't need to confuse. Just I show you just now. Okay, just I would like to show you just now. Okay, the resistance and the overall area, normally you consider for one area, okay, in order to avoid that confusion. And for the effectiveness is multiply with the number of dead tubes. Okay, so this is step number 2, step number 3, this is step number 2, this is step number 3. Then we go to step number 5, right? So for effectiveness, since you have 200 tubes, so you must multiply with 200 tubes here. Okay, you must multiply with 200 tubes here. So that means the overall coefficient, you get the overall coefficient is the overall coefficient for one tube, but the area here is the overall area. Okay, then you will get 1.2. So if both UO, AO over C mean and UI over AI, UI, AI over C mean are the same, so that means you have the same answer. If your NTU calculated either using UOAO or UIAI is different, then you have a wrong answer. Okay, so I hope you already understand or you have no confusion anymore. So that means, I repeat one more time, the overall coefficient and also the resistance, this one you must consider for one tube. Okay, so that means one tube means the area for one tube. Okay, meanwhile for the effectiveness, okay, you must consider the total number of, okay, the area is for the total tubes. Okay, so that's all for tutorial 7. Okay, or maybe I can show you some miscalculation last time. Okay, so just to avoid confusion. Okay, so TCO obtained for tutorial 7 is 101. So in tutorial 6 last time, the TCO was 80 degrees C. Okay, so this shows that when you use 200 tubes, the TCO increase. Okay, because TCO 80 degree was only for, this one is for one tube. Okay, this one is for 200 tubes. 200 tubes is this one. So you see that the temperature increase. So it shows that when you have higher number of tubes, so higher rate of heat transfer, which it can be shown here, and also the outlet temperature of cooling fluid also increase. Okay, so meanwhile the outlet temperature for heating fluid is 102.7. Okay, and last but not least, okay, last time my drawing was not so clear, so I redraw it for you. So when I redraw for you, you see that actually this is showing only one tube. So one tube has inner diameter. So this is inner diameter. Okay, and this is the this one is the outer diameter. Okay, inner diameter is inside, outer diameter is the outside. So because of that, it has this what we call the thickness of the tube. Okay, so the shell is here not shown. Okay, so all this tube is actually in the shell. So this is the fluid in the shell. Okay, so since the fouling occurs on the inner side of the tube, so inner side of the tube is one. Okay, the blue one, and also outside of the uh, outside of the tube, which is facing the shell. So this is outside of the tube. Okay, the red fouling. So therefore, if I want to show you the total number of resistance, okay, maybe I can show only the half of the cylinder. Okay, so without any fouling, we can consider only resistance due to convection inside and convection outside, as well as the due to the resistance of the wall of the tube. Okay, but when you have fouling, okay, so just now I mentioned about without fouling. So without fouling, you have, this is 1, okay, this is 2, the R wall, which is R conduction, and this is 3, which is resistance due to convection inside the tube. But when you have fouling at the shell side, because this fouling is facing the shell side, then you have another 2, which is A here, okay, and fouling here. Okay, so this is B. So this is A and this is B. So that means altogether you have 5 resistances. Okay, if you have fouling. Okay, I think that should be it for tutorial 7. If you want to break, just press pause. Otherwise, you can just continue this because now we want to discuss on the previous final exam question which I have shared with you. Okay, actually, this is the question for, I think, if I'm not mistaken, 2016. Okay, so in this case, maybe you can read the question. I think you have already read the question. So the question asks you to find about heat exchanger, which is double pipe. So double pipe means 1 and 1. Okay. And actually the surface area is given. And is it this heat exchanger thin wall or thin wall or not, we will see. Okay, it is not stated here, but it is just stated that it one it is for the wastewater and also fresh water. So which one is the cooling fluid now? Okay, because uh, the wastewater here is used to increase the temperature difference of the fresh water. So that means the fresh water here is the cooling fluid. Okay, maybe I can change the color. Okay, fresh water here is the cooling fluid, and the uh, wastewater here is the heating fluid. Okay, so the CPs are given for both fluids, and the temperature difference for fresh water is 26.4, and the overall coefficient is also given as 625. Okay, the first one is if the rate of heat transfer is given, what is the mass flow rate? Now, we can write down all this information. As I mentioned just now, wastewater is the heating fluid or the heating stream. So, the mass flow rate is unknown. Okay. The mass flow rate for cooling stream is also unknown. Okay. Then, uh, here it is asked that CP are given, outlet temperature for heating stream is unknown, okay, but for fresh water, okay, the temperature inlet and outlet is not specifically given, but only the temperature difference was given, okay, 26.4. So we can write down that uh, the outlet temperature is equals to 26.4 plus TC1, TC inlet. Okay, so what else? I think, okay, this is double part. So we can see the next step. Okay, we need to find the mass flow rate. Okay, okay. Here it is given that the mass flow rate of the heating stream and also cooling streams are the same. Okay, same mass flow rate. So then what we can do is, okay, we can calculate using this equation. Okay, Q for the cooling fluid is equals to its mass flow rate multiplied with its heat capacity and the temperature difference. Here, because we know the temperature difference, okay, then we get the mass flow rate of 0.31. Since the mass flow rate was the same, okay, same mass flow rate was the same, so we could say that the MH here is also 0.31. So for this one, you get 4 marks. Okay, next, the B. B is you need to determine the outlet and inlet temperature of fresh water. Okay, so first, tip is given. First, the outlet temperature of waste dying water need to be determined. Okay, so that means you need to determine firstly the TH out. Okay, so now we know that Q is equals to 35,000 watt. So this is given. Okay, so since the mass flow rate for heating fluid was obtained in the step A, okay, you can put that value Then you rearrange the equation. Then you get the outlet heating fluid is about 49.3. Okay. So to calculate the THO and TH out, so what you need to do is, so first of all, you can use this method or you can find another method which you find more easy. So you know that the delta T log mean here and the F value is actually 1 because this is a double pipe heat exchanger. So this value is 1. Okay, the overall coefficient is given, the area is also given. So we get the delta T log mean is 33.9. Okay, then, okay, because Q, U, and A are known, all these are known, then we can get the delta T log mean here. So what we can do is we plot the temperature profile here. Okay, so the temperature profile for heating fluid, the inlet is 75, the outlet is 49.3, which is already determined. Okay, the TCI is unknown. The TC out, uh, as we know that there is a temperature difference of 26.4, so TC out should be equals to TC in plus 26.4. Okay, now we can calculate the delta T log mean, okay, which is delta T1 minus delta T2. So what is delta T1? Delta T1 is 49.3 minus TCI, and delta T2 is 75 minus TC in and also 26.4. Okay, so when it is minus TCI and 26.4, we get it is equals to 48.6. So we put delta T1 and delta T2 here. Okay, here you can simplify the it is only mathematic. Okay, you can cancel TC1 at the top and you are left with TC1 at the bottom. Okay, you rearrange this equation and then you can get the value of TC1 equals to 15.04. If I'm too fast, you can pause me. You can press your own calculator and see whether you get the same value as mine. Okay, then when you get TC1, you can directly calculate TCO because TCO is TC inlet plus the difference, which is 26.4. So you get 41.44. Okay, so that means we are complete with part B. Next is part C. Okay, after several years, the effectiveness of the same heat exchanger is only 38% due to fouling. Okay, determine the fouling factor that occurs under this condition. So, if you still remember, this is the definition of fouling factor, which is actually the uh, the difference between the inverse of overall coefficient with fouling minus the inverse of the overall coefficient without fouling. So this one is without and this one is with fouling. So as we know that in the very first place, the overall coefficient given was 625 and this actually represents the overall for the clean heat exchanger. So we can refer to the graph which is also provided together with the exam question. So now you know that if you see here, effectiveness is given as 38 and then you know already the C-min. You can calculate C-min, and area you can also calculate, or no, area is already given, so you can find the coefficient for the dirty heat exchanger or the heat exchanger with fouling. So what we do is now we want to calculate C-min. Okay, so we first find out which one has C-min. Okay, so is it from the heating stream or is it from the cooling stream? So from here we see that the cooling stream has lower joule per second Kelvin. So therefore we can consider this as C-min, and for the heating stream as the Cmax. So the ratio is almost 1, or the ratio is 0.97. Okay, so it is almost 1 here, 0.17, and the effectiveness is 0.38 or almost 4. So we can just draw like this. Why I get, oh, no, I was wrong, sorry. It should not be here, right? 0.38 should be here. Okay, somewhere here. Therefore, I get about 0.5. Okay, so when everything is known, only U is unknown. So this U here, because this is the effectiveness after fouling, so you can calculate U for with fouling. So this is the dirty. Okay, so my D is not so good. This is actually the dirty overall coefficient. Okay, you can calculate it, and after fouling you get the value of 401. You see that the overall coefficient becomes lower, okay, if it is with fouling as compared to without fouling. Then you can calculate the fouling factor. If you just take this value, then you will get the fouling factor with m squared here, because you just inverse the unit of overall coefficient. However, you can also divide this with the area, then you get the fouling factor only as degrees Celsius per watt, and this is about 5.38 or 8.9 times 10 to the power of minus 4 meter squared degrees Celsius per watt. So both are acceptable, but you have to refer on the question, because in this question it is not specified the unit for fouling factor. Okay, if it is specified without the area unit, so that means you have to divide with the area itself. Okay, and last but not least, this question also asks you what are the common causes of fouling in heat exchanger? How does fouling affect the heat transfer and pressure drop? So I think this one is 2 marks. I don't want to discuss here. You can always read and find the answer or in some other references. Okay, so far I have covered you the tutorial 7 and previous final exam. You can break if you want, but I just want to continue a little bit. Okay, so this is exercise 1. Okay, this is actually taken from the lecture note. Okay, actually you can go through. This is actually very straightforward, and This is actually very straightforward. It is double pipe, and uh, here the pipe is not a thin wall, okay, because the diameter is given as outside diameter, and also, okay, sorry, this is inside diameter, this is outside diameter, okay. And then what else is given? The H coefficient for inside and coefficient for outside, and fouling factor was also given. Okay, then the question asks the thermal resistance of heat exchanger per unit length, and also the overall heat transfer coefficient. So I think the answer here is only given for the B. Okay, I think if you get B right, you should get the A right, because this is the relationship between the resistance and overall coefficient. So if you get the answer for B right, so your A should also be right. Okay, so I think you can already know how to answer this, because first you need to draw. Okay, so then label. Okay, then find the total resistance. Total resistance in this case, there are 5 resistance. Okay, inside the tube through the fouling. So, but let's see, the fouling on the tube side and also on the shell sides are not the same value, so you should be careful on that. Okay, and also fouling due to not fouling, sorry, resistance inside the tube 1, resistance due to fouling inside the tube 2, resistance due to the wall 3, resistance due to the fouling outside tube or fouling at the shell side 4, and also resistance at the shell side. So altogether you should have 5 resistance. You just add on everything. Okay, then at the end you can calculate the area for the tube, and the area for inside area and also for outside area. Okay, AI and also AO. Then using this relationship, you can calculate the overall coefficient for the inside and for the outside. Okay, if your answer slightly different from this one, it is okay, because sometimes the decimal places plays an important role, but that's fine. I'm going to accept that if it is not so far away. Okay, so for exercise 2, you want to discuss on the exercise 2? Okay, so let's see. For exercise 2, so first of all, we see that this is also a shell and tube heat exchanger. And this heat exchanger, we can assume that it is 1-to-1. When it is not given, then you can just always assume it is 1-to-1 or double pipe heat exchanger. So the flow rate given for both heating and cooling stream, and temperature given. So if this is given for inlet and outlet for heating stream, so you can use either NTU or LMTD method. And this is also given for cold water. Okay, then you need to calculate the area. So this one is actually the same step, like, because U is also given. So this is like tutorial 6. Okay, exercise 2, you can refer to tutorial 6. Okay, the how to solve. Okay, tutorial 6. Okay, so this one you can flexibly choose either tutorial 6A or B. Okay, because A is LMTD, B is NTU method. Okay, then exercise 3. Okay. You can pause if you want to read the question. Okay. Um, as for me, I already read the question, so I just want to show that this exercise 3, how you can solve this is you can refer this using step or tutorial 7. Okay. So if you refer tutorial 7, then you can solve exercise 3. So, okay, so for exercise 3, you have different BWG tube. Here is BWG with 25 mm outside diameter, and it is BWG 14. So from this um, table, it should be this one. Okay, then 21.18 is the inside diameter for these tubes. Okay, how many tubes are there? So there are only 50 tubes, while for tutorial 7 you have 200 tubes. So the steps are the same. Okay, exercise 4, how we can do it. So let's read for a short time. So here actually you need to find the area. So from the information given, from the information given, actually I believe that you can refer either tutorial 6 A or B. Okay, but this one you have exercise 4A is for counter flow, and exercise B is parallel flow. So you should do both if you want. Okay, so if you want to see whether you get it correctly or not, you can just refer to tutorial 6, the steps how to solve this exercise 4. Then exercise 5. Exercise 5 is not 1-to-1, not double pipe, but it is 2 for heat exchanger. You need to find the surface area. So this one also actually should be, we follow tutorial 6. Okay. And this one, the only difference is that it is using the British unit. Okay, this is one. Secondly, only the inlet temperatures are given. So it is 475. The outlet temperatures are not given. So what you can do for exercise 5 is actually you can refer to tutorial 6B only. Okay, so that means it is using NTU method. Okay, what else we don't have here? So it is between water and okay, both are waters. So in this case, the CP is not given. If CP is not given, you should interpolate. Okay, you should interpolate the CP. So at which value? At average value. So how to know what average value? So you need to estimate the average value. Then only from there you can interpolate the CP value. Okay, so you need the CP for both heating and cooling fluid. Okay, so here is the area you need to find. Okay, now The next question is whether this area you need to multiply with 4 or not. I think you already know the answer. The answer is no, even though it is not indicated in this case, because the area here should represent the overall area. And it is also not given whether this is parallel or counter flow. If the question does not give you whether counter or parallel flow, so you should assume as the counter flow. Okay. And last but not least, we have exercise 6. Okay, exercise 6, I think maybe we can do it together. Okay, so first, maybe you need to read the question, and then maybe we do exercise 6 in online class. Okay, maybe you can try to do this on your own and discuss this during online class instead of recorded tutorial. So that means you have for tutorial for heat exchanger only 3 parts: part 1, part 2, and part 3. Okay, so with that, I have no more to say for tutorial heat exchangers. So, oh no, I do have one more tutorial for heat exchangers. Sorry. Actually, this is exercise 7. Actually, we already discussed this because okay, because actually exercise 7 is same as example 1. Okay, so you can do this on your own. The only thing that we want to discuss during online class is on the exercise 6. Okay, thank you very much.